So for the next hour, we're going to hear from 3 of the key technical development leads within the GNU Radio project, Sebastian, Martin, and Nathan. And they'll be talking about 3 different areas, GRC, Sebastian's, Volk from Nathan, and PyBombs and Cgran from Martin. So I'm going to hand it off and let Sebastian take it away.
Okay. All right, so I'm Sebastian Koslowski. Before I get started, I work at the KIT in Karlsruhe, Germany, which is sponsoring my trip. This is why I'm mentioning this. And I'm here to talk about the GNU Radio Companion. Now, you probably all have heard about this in the previous talks, but I'm starting off with this basic assumption that you don't know anything about it. So we'll just can get everybody on the same page. A bit of history on this, and since I'm not seeing this here, the GNU Radio Companion is part of the GNU Radio project or the source tree since around 2008. It was previously developed outside of the tree by Josh Bloom. Yeah, it's been extended and tinkered with by many since then, and if you pull the Git logs, there's about 45 contributors, but most of the commits are from a very few people. I took over maintaining this part of GNU Radio in 2013. And just to continue the background of the software part here is it's written in legacy Python right now, which is Python 2. We're using GTK2 XML files, which I'll be talking about in a bit. We use Cheetah as a templating engine because, like Jonathan mentioned, we're generating Python code, and we need a templating engine for that. Current work on this is just making changes and updating stuff that has been there a long time, GTK versions, Mako templating, and YAML config files. All this stuff will be part of my talk on Wednesday, so if you're interested in that, I'll get into detail on those parts then. Now, what are we dealing with? So we have a user interface to design radio applications. We call them flow graphs, and they're basically those graphs with nodes, which are DSP blocks. They're used to process inputs they get on sync ports, and they spit out data at the output, which we call source ports. So aside from that, we have edges between the nodes, and we call those connections, and there are different types of connections. You've heard of stream connections, which are basically used to process a continuous stream of data by various blocks, but we also have asynchronous message connections, and we also might have all different connections. As GRC is concerned, we're abstracting that to the underlying radio features, or features that may come from external modules. The second part of the application is the actual code generation. Now, once you have that graph in place and you set up all the functions you want to have, you hit generate or you hit run. Does both the same thing. It generates either a Qt GUI application, a command line application, or another block that can be used in yet another radio application. We call those hierarchical flow graphs. Now, in most of your distributions of GNU Radio, there still is the VX GUI, which is deprecated now. So with the next GNU Radio release, we'll no longer have that, but I'm just mentioning it. This is the 4th generate mode. Now, this is the GUI as it is today. We have in the middle here the main canvas, which is used to draw up blocks and ports and connections. On the right-hand side, we have the block library, which is a tree of blocks that is loaded and known to GRC. This is mostly the core blocks, and underneath that, there's outer tree modules and their blocks. Each of these can have a category, and what you actually do is you pull stuff in and then connect it. On the lower side here, there's, on the left hand, the console, which is kind of use like a mixture of logger and output of the running flow graph as it stands today. And on the right-hand side, there's a pretty new addition. This is the Variable Explorer. So I'll be talking about variable blocks in a bit, but this is actually kind of a, let's not call it experiment, but it's a new way of managing variables inside the flow graph. Instead of keeping those blocks around, you can have them nicely organized in this tree. All of those panels can be hidden or even moved sometimes. This is the basic GUI. And what you can do now is you just add blocks to that. And I will be working with this simple example flow graph today, where we have a noise source. So it's a generator of data. It has only an output port, a source, which connects to a throttle block, which we generally use to limit or rate limit the data that is passing through. It does nothing else but copy data at a fixed rate, so I'm not overloading my processor. Next is a low-pass filter. And then there's a Qt GUI frequency sync. What you can see here is all of those blocks sort of have different parameters. And you'll notice that some of them are the same. They're reused. Then I have another block right here that has no connections whatsoever. This is another kind of variable. We'll see that in a bit. So the main thing that GRC does is model the behavior of the blocks that you later want instantiated in your Python code. And for that, there's the ports. Now I'm just going to run down all the options you have. I'm not going to do the whole tutorial thing where I explain how each feature works in detail, but I just want to give an overview of what's possible. So if you want to write a block representation in GRC that's a little bit more capable or dynamic, then these are the tools you have today. So ports represent, as I mentioned, streaming or messaging I/O of blocks. And there's various ways we can go about this. The standard stream ports have a data type, which is indicated by the color, and they have a vector length, which is indicated by the shading, as, for example, down here. So when we connect ports, we usually connect them by the same color, but it's not necessarily required. The underlying radio application only requires that the item size matches, and this is the product of those two. So this part down here is a completely valid but obviously useless flow graph, which generates nothing and copies it, but casting into different types. It all works as long as the item size matches. Now, what else can we do? Say you have a block or want to write a block that takes a variable number of inputs, like an adder block. And so GRC has the ability to clone ports. So if you wanted to have 4, then 5, or say 10 inputs, you can just clone the single port and just add them up, like we have here in this example. Another pretty useful thing is the concept of hiding ports that are not required in a certain mode. Like here, I have enabled the third copy block to have a message input that actually changes this parameter. And I just connected the message trope here so you can see what it looks like. It's not really useful or anything. But you can see the normal streaming data passing through this path, and then there's a control path on the lower part, which is usually how you can organize things. So the main two features here are copying of ports and hiding of ports, which can then be used to generate arbitrary wrappers around different DSP blocks. The other important part or core part of the model is how blocks are configured. So we usually have options to configure the block itself during runtime, certain parameters like the FFT size or a set of filter tabs. But we also have parameters to control how GRC displays your block, the number of ports, for example. Most blocks you'll encounter have just the constructor arguments as parameters, and then you get a nice widget built like this, which lets you enter those in each instance of your block on the canvas. And then once you hit run, they'll get plugged in and it'll work. But the interesting thing to notice here that I can plug in any Python expression in here. See, I've dividing and multiplying stuff. That's no problem. Since we're designing a Python application, we can plug in any Python code in there. It's a single line, so it's only an expression, and it can get messy if you want to put a lot of code in there, but that's usually not required. If you want to do computation, you can do it outside of it, and then just plug the results in here using a variable. You can also import additional models. A lot of radio applications out there do that. For example, you keep one Python module where you have all your constants, your config. You can even switch, and then pull whatever you need from that in the different parameters of each block. Now, for the dynamic stuff, if you really want to write a nice block wrapper, you can selectively hide parts of these parameters. Say if I choose a different window here, I may not need this beta parameter. Has no purpose. So I just hide it away. Or the mode I'm running this fear filter on, it's not really that important that I have to clutter up the canvas, so I'm hiding it from here. Those are all possible. These GUI widgets here are not only raw Python inputs, but you can actually have them type checked. So you declare a parameter not as raw, but maybe it's a complex. So GRC will complain during the validation stage if you enter for the decimation, say, a negative number. You also have block level checks for ranges or combinations of parameters. In this case, it wouldn't make sense to have a cutoff frequency higher than the sample rate. Could do it, but why? All this shows up down here in this little area. And well, while you're designing your application, it's basically the job to keep this empty. There's also the option of scattering the parameters over multiple tabs. If you have a block that has a lot of options, it makes sense to just split these into categories and have different tabs. The advanced tab, which is shown here, is generated by GRC itself and contains sort of the built-in stuff that Radio lets you set for each block. There's also a nice feature there which lets you enter a comment in there, which will be shown beneath the block in the canvas. So if you want to kind of document your flow graph, or if it's for educational purposes, you can add comments there, and they'll show up in the canvas, and you can add documentation or explain what blocks do. What you can also go ahead and switch to the documentation tab. This tab contains whatever gets pulled from either the block wrapper, so if you write your own block and you can put documentation in there, or the Python class that is represented by this block. Whatever doc string is in there, pulled from Doxygen or even the C++ source, may show up in here. This is a fully automatic process, so if nothing's there, then the block offerer has not put anything in there. The last step here is the generated code. Some people really want to see what will happen in the resulting file, which can get pretty huge. So this tab will only show that part of the code that belongs to that block. Mostly, this is an import line and a line that instantiates the block. But for variables or GUI widgets, there's a lot of more code, so you can get a better overview. The next concept I want to talk about is what kind of makes this more than just connecting stuff and just generating code. And those are flow graph variables. So what we're basically doing here is we import required models, we generate block instances, we connect them up, and then we hit run. This is what the generated code does. But there's more you might want to be doing. And this is use variables to not only configure blocks, but also reflect a certain runtime state. So we use variables to plug in constant values, but we also have variable blocks that change during runtime. And we can have blocks updated when their value changes. Those are called callbacks, and each block has to specify callbacks, basically saying, if this changes, call this setter on me, and then I'll update my state. So we have different forms of variable blocks. The basic one is this one. You have seen this before. You just give it an ID. That's the name it'll have in the Python namespace and all of your flow graph, and you enter a value. That's a simple Python expression. But then we have others. There's first of the parameter block, which is used in two ways. If you're designing a command line interface, then this will be the command line arguments. So it'll generate an argparse definition for that, and you can, when you start up your application, pass it a sample rate or a cutoff frequency, like in this example. You can also have a variable be driven by a GUI entry widget. In this case, it's a simple range selector. So when the flow graph is up and running and I move this about, the variable changes and the setters get called and something actually changes. Other ways is more for convenience of development. Say I have multiple filters that use or share the same tabs. I could use the variable block, the filter block I had before, but then the tabs will get generated on each instance separately. Or I'll have a variable that represents those tabs. They'll get calculated once, and the resulting vector can be plugged into the filter blocks. There's also arbitrary objects. Basically, all of these two, they just have a factory function beneath them that generate any Python object that will be then available to other blocks. This one here is used in the forward error correction module of GNU Radio. It's a definition of an encoder object that will get passed to the actual block that does the processing, and it's generated right here. Other features I would like to quickly mention is, of course, we have the library of blocks, but it's really easy to extend that. We have tooling. You can write the XML manually. Whatever you do, it'll get integrated seamlessly. So there's no special treating of core modules. Maybe we will add features easier for core models than for other people, but other than that, they're treated exactly the same. You can group blocks with hierarchical blocks. Mentioned that before. So if you have a DMOD chain you want to use for multiple channels, you just put that in a separate block. It'll get its own set of parameters in and output ports, and then you can just instantiate that multiple times. This is also a concept that's directly copying the underlying radio higher block type. So this is not really GRC specific. What is specific is the next section, and this is really important if you're just starting out with GNU Radio. Like we have this whole tool chain of you get a skeleton for your C++ code, you write a work function, you get that build, you get the wrapper for GRC, and finally you can use it. If you just want to try something out or get started and just want to experiment with stuff, we have the ability to create and edit Python-based blocks directly from GRC. I will get into the details of that in a bit. Other thing I want to mention is the integration of custom processing domains. So if you not only want to do the work on the CPU, but maybe on an FPGA or a DSP, you can actually define a custom domain, which will change GRC's way of connecting blocks if you have ports in that domain. So you can have a block operating on the host port, on the host PC, and say a block that operates on the FPGA. And the connection between them can't be a simple buffer because it's a different processing domain, so there has to be some additional stuff working, and What actually has to change in GRC from the perspective of GRC is a different kind of connection code has to be generated. And this is what domains are for. So if you want to have custom connects or custom domains, you can talk to me about this one. Arithnoc is the prime example of this feature. All right, finally, we have everything done. And then we can hit generate and run, and we'll get this nice GUI application generated for us. So we have the Qt GUI range, which is a flow graph variable. And we have the Qt GUI frequency sync. Those will get arranged beneath each other. By default, you can define other arrangements or tabs, whatever fits your needs. And then actually move the slider and just get the change. And this happens through the callback feature. So just to reflect on that, the cutoff variable, it's just there. Its value change won't affect any blog directly. But since during generation, we know that the cutoff frequency is actually plugged in here, code will be generated that calls the setter for the cutoff frequency on the low-pass filter block. This is stuff that you don't have to really care about, except when you're writing your own block and you want that behavior, then you'll have to notify or make that known in your wrapper that you'll have that callback and you want that feature. Okay, how am I doing on time? Okay, so the extra stuff. Embedded Python blocks, just want to get in a bit more detail on those. I really recommend people who are new to this to check it out. It's a way of quickly trying something or just getting the feel of how it's going to be to do custom DSP. Drawbacks is you have only a Python implementation of your block, which can be slower, but you can use NumPy and all the Python DSP stuff to get work done. And the nice thing about is that you don't have to care about block wrappers, integration, and anything. You just drop the Python block in here, open its properties window, and click on this button. It'll open your editor. You can choose which one to open. And you get this standard GNU Radio Python block, which you can edit. I have added some extra parameters here. I have declared an input and an output port, and I registered a message port. And once I save this, all this here will get updated automatically. So you don't have to worry about specifying anything. You can basically just write the code, hit save, and it'll get updated instantaneously. So if you want to get started with this, this is the easiest way to do it. All right. With this, I'm actually going to close my talk. I guess we don't have time for questions, but maybe one?
While I switch,
yeah, I'm really curious on the internals of how the scheduling works inside of GNU Radio and how the messages are passed back and forth. Is that included in some kind of documentation or presentation, or so we know how these blocks interact to do performance tuning?
Okay, so this is definitely outside of the scope of GRC itself, because, well, but you can check out our documentation. It's a Doxygen-generated page. There's lots of information about this. The scheduler itself has, I think there's a presentation from Tom a few years back that's pretty comprehensive.
Hello? All right, there we go. Just to jump in real quick, Tom actually gave a presentation on this, and I have no idea where that question came from. Hi. Tom actually gave a presentation on this, and I know the slides are online along with documentation. I think there's also a blog post about it. I'll let you finish that.
Yeah, so if you go to my blog, just trondo.com, find the blog post, or I forget where it actually is. Honestly, if you look up for this question on the mailing list, it comes up a number of times, so there's a number of links out there. Maybe it's even on the GNURadio.org page somehow. So it's a pretty extensive set of slides. on the scheduler and kind of more details into it. We've given presentations on this. Myself and I think Jonathan Corrigan have dived into this at variations on various levels for the message passing, the stream tags, the scheduler itself, this and that. So there's definitely a lot of material out there from previous conferences and on my website.
And just for further detail on stream tags and message packet passing in particular, Tim O'Shea, who's one of the developers and also one of the sponsors, this O'Shea Research, has done a lot of work in that area, and he has a lot of blog posts and documentation about how all that works. And he wrote a significant portion of that infrastructure. And he's also here. Tim, are you in the room? No? Oh, he's in the RF Knock tutorial. Okay, yeah. But feel free to ask us if you have any other questions.